right, now that we have talked about the cis and the trans alkene, and we briefly talked about the stability of those trans being more stable, and I said, sterically speaking, the groups are far apart from each other. This is a good time to talk about the comparison of stability of various different isomeric alkenes. So, for example, comparing 1-butene to 2-butene and the likes of that. Now, one might consider that if you had to interconvert, let's say, a cis isomer into a trans isomer, okay? Now, the interconversion, when I say interconversion, that means going from the cis perhaps to the trans molecule. So maybe you started with cis-butene, you subjected that to acid catalyzed condition, maybe you provided some heat, and you're hoping to get a trans alkene out of it. This reaction is not going to take place spontaneously. Even though trans molecule is more stable, it's not going to just happen on its own. You have to make that happen. Any guesses on why that is? If you're thinking that that's got to do with the stability of the double bond, you're absolutely right. Bang on. And good job thinking about that. That double bond imparts a greater level, a greater sense of stability to the molecule. And so, and once that reaction kicks in, once that reaction takes place in the presence of the strong acid, you would find that the stability of the two compounds essentially at equilibrium is going to be different. So cis is going to be far less stable as compared to the trans, okay? And so they are not of equal stability. And when I compare my two molecules here, notice cis is only 24% in my reaction mix. Majority of that is trans. So it is predominantly the equilibrium is towards the trans molecule. And of course, that's got to do with the stability that we have discussed previously, that the steric interference of the two groups that you have, you would want to place them far apart from each other. So if you had a cis molecule and you wanted to subject that to treatment with an acid and heat it, it's going to be directed and get converted into the trans, but that initial trigger will require some work. That initial trigger will have an activation energy. So think about those things that you already perhaps have seen in the past. Now, one general method of determining this is through the hydrogenation reaction. So basically what that means is that irrespective of the kind of alkene that you're dealing with, upon hydrogenation, which basically means that you would be treating that with H2 and a catalyst like palladium or platinum, sometimes radi-nickel. And so we are hoping, we are expecting that our compound is going to go through a reduction reaction. So let's say I have a 2-butene and I treat that with H2PD. It should give me an alkane. And if I have a trans molecule with hydrogen palladium, would also give me the butane molecule. It's the same product that is getting formed by both of your starting alkenes. But there is a difference between the two alkenes. And that difference is that whichever is the less stable of the two, that will give off more heat. Again, whichever is the less stable of the two will give off more heat. Let's take some of these steps, these things in stages, and we'll discuss about each of these bullet points, what those mean, and take it from there. Heat is typically given off when the C double bond C is converted into a single bond. So when you compare your cis molecule as undergoing hydrogenation, so what I just said is that irrespective of whether you start with cis-2-butene or trans-2-butene, your product is butane, and this graph essentially shows you that. we are saying that irrespective of which one you have, the amount of heat that is getting generated is going to be different. Even though they were butenes, these were two different types of butenes to begin with. And since this was at a higher overall reaction, right, a higher energy, since your product is the same, butane is your product, the net difference that you see is going to be bigger, greater as compared to the difference between the trans and butane. In other words, more stable alkenes give off lesser heat of hydrogenation. More stable alkenes give less heat of hydrogenation. So very specific result there. Just to put numbers for this, when we have cis to butene, the amount of energy that is given off for the hydrogenation reaction, the delta H naught is negative 120 kilojoules per mole. So it's telling me that it's an exothermic reaction, which it is, and it's telling me that it is giving off the delta negative 120. And it's telling me that if you have trans, then in that case, your delta H0 is going to come out to be negative 116 kilojoules per mole. So we want to make sure that we kind of call out on this, that your cis molecule, which is the more unstable of the two, will have the higher heat of hydrogenation that will be given off, since it started at a higher energy level. Trans, on the other hand, is starting at the lower energy level. We are seeing that here. Hence, the amount of heat that will be given off to form the butane would also be lower. One of the factors for this stability, one of the bullet points said that a tetrasubstituted alkene is going to be more stable than the trisubstituted, which will be more stable than the disubstituted, and finally the monosubstituted. So what factors do those depend on? So tetrasubstituted would mean that all four positions on the double bond are taken up by anything other than hydrogen. A trisubstituted would mean that you have three groups. A disubstituted would mean, and really disubstituted could be of two kinds. And I'm showing that they're approximately equal, but they may differ a little bit as well, which we will talk about. And then the monosubstituted, which means that there's only one alkyl group out of all the four positions possible. Okay, so what we are saying here is that the stability of the substituted alkenes, this is due to the combination of two things. All right, one is the stabilizing interaction between the carbon-carbon pi bond and the adjacent CH sigma bonds on the substituents. So in other words, this has a word to describe as. It's called as hyperconjugation. Hyperconjugation means that there is going to be a bonding molecular orbital which will somewhat extend over four atoms in the double bond. Let's take a closer look as to how that would be. So for instance, we are saying here that you have a carbon, another carbon, we have the p bond, right? And that's the pp overlap. And I'm just going to consider one at a time. So let's say you have an R group. Maybe that group is a methyl group. So if it's a methyl group, hopefully you can see that that would be sp3 hybridized. So in a sense, this is going to look like a tetrahedron where you're going to see the hydrogen, the hydrogen, and the hydrogen. And here you're going to see the sp2, right? That's the overlap. That's how the sigma bond got formed. That's the sp2. This is the sp2. And the pi bonds are essentially getting formed this way. So what happens is that your CC pi bond that you have, so your overlap that's happening between these two, that starts to extend to one of the sp3, whichever one of them. So one of the sp3 hybridized CH bonds. So it's kind of extending, it's going beyond what is allowed typically. And so instead of having a two atom affair, it becomes like a 4-atom affair in which the CH bond of the neighboring CH3 is also participating in an interaction. And the only reason that that happens is because the plane in which this p orbital, and that sp3p orbital, that's pretty much the same plane. And because of that, this is seen. A second factor that contributes, which kind of stems from this, is the alkene stability involving the bond strength. The bond between an sp2 carbon and an sp3 carbon is somewhat stronger than the bond between two sp3. And you could perhaps imagine that, because when you're looking at an sp3, you're looking at more or less a single bond, right? On the other hand, when you're looking at an sp2, it has a greater S character. It's closer to the nucleus. It's strongly held and tightly held, and also is more stable, right? So if you want to compare, for instance, if you wanted to compare, let's say, one butene, 1, 2, 3, 4, and you want to compare that to 2-butene, and we are going to take a look at what kind of bonding is present here. So you would say that in your 2-butene, for instance, you have the single bond, which has an overlap between sp3, sp2. There is another one which is sp2, sp3. And of course, in the middle, you have the sp2, sp2, right? In case of the double bond, however, you have this, which is sp2, sp2. This guy is sp2, sp3. And this one is going to be purely sp3, sp3. So 3 different bonds, and they are essentially 3 different kinds. And I just said that when we have an sp3, sp2 bond overlap, which is typically, that will be present, we have 2 of those at least here in the disubstituted case, the 2-butene case. The highly disubstituted alkene in this case will have a higher ratio of the sp3, sp2 bonds as compared to the sp3, sp3 linkage. And so it is more stable. So one could say the takeaway from here is more number of substituents lead to higher sp2, sp3 linkage with higher S character, more stable bonds, and hence the alkenes overall, which contain more number of these sp2, sp3 linkages, are going to be considered more stable. So that's one. The other is hyperconjugation, where we are saying that the double bond is not just located and localized for or in between the carbon 1 and carbon 2. It's not just between carbon 1 and carbon 2. It's actually extending to a third carbon, to the methyl group in close vicinity, which is why sometimes hyperconjugation is also called as the no bond resonance. The word no bond resonance basically shows us that again, we are looking at over here an sp3 hybridized orbital, and this was our sp2. Notice the planar shape. The p orbital is showing the pp overlap, and it is the pi bond which is getting extended. It's an extended resonance, if you will, which is not a formal bond. It's not a formalization that you see, but rather the plane of this sp3 is going to be in the same plane as the remaining p orbitals, which is why that is possible. And because it's a weak bond, it's not that only one such orbital can do this. You can actually see that with the other hydrogens as well. So here is the electron density map for that. Notice how your double bond is essentially in the planar shape, and your p orbitals would have been up and down, and you have your sp3, and notice how the electron density has kind of increased over. This is proof of that. And whenever you would have essentially movement of electrons using these electron density map, we can see the strengthening or the stabilization of those molecules. So having alkyl groups right next to the double bond ultimately leads to the stabilization of your antibonding pi orbital, and it's considered a positive interaction overall. So here I have three different pair of molecules, and we have to tell which one of them are more stable. And as you can see, that the very first one, that's a mono-substituted alkene versus a di-substituted alkene. So more is the number of R groups, one could say that greater will be the number of sp2, sp3 groups, and that is going to stabilize that alkene more than otherwise for both hyperconjugation as well as more number of sp2, sp3 linkages. So this guy is going to be more stable. In the second case, we have cis versus a trans molecule. In case of trans, the big bulky groups are far apart from each other, which due to steric reasons, you would say that trans is more stable as compared to your cis molecule. The last one, again, you're looking at a tri-substituted alkene versus a di-substituted alkene. And you have tri-substituted, which is more stable than the di-substituted because, again, more number of sp2, sp3 linkages that might be present in the molecule, increased number of R group, greater level of hyperconjugation. Let's consider the general reaction mechanism of an electrophilic addition reaction. Couple things here. We are calling it electrophilic addition because my double bond is serving as my nucleophile. Absolutely. Let's say I'm using HBr as my electrophile, okay? And we know that HBr, since it has that polar bond, bromine is going to be slightly negative, H is going to be slightly positive, the bond can be polarized, and all of that. We know that. So one can say that the reaction will basically begin with the attack on the hydrogen of the electrophile by the electrons of the nucleophilic pi bond. So what we are suggesting here is that the two electrons in the double bond, those two electrons from the pi bond are going to form a new sigma bond between the hydrogen and the alkene carbon. So that's what I'm showing by this bond A. And as that happens, essentially as that double bond breaks, the bromine is going to leave as the bromide. So know that the electron flow is unidirectional. So you always bring in a couple things to think about. You always bring in your nucleophile to the electrophile. So it's the source of the electron which moves the arrow to the sink of the electron, not the other way around. As you're doing that, you have to make sure that your your atoms follow Lewis theory. So you can't have 5 bonds coming out of hydrogen atom, for instance, right? So you have to keep that in mind when you're drawing the structures. Now, the resulting carbocation intermediate that is generated, that itself is an electrophile. Notice the positive charge on the carbon. And that's where your incoming bromine is going to attack as the bromide, and that gives rise to the generation of the 2-bromo 2-methyl propane. So one could say, if I were to show that without the p orbital, one could say that I'm starting with 2-methyl propene. One propene would be a little bit redundant, but you could if you wanted to. I mean, that is one. And you're treating that with HBr. You're showing the bond starts with the double bond. It ends on the positive charge of hydrogen, which causes the bromine to go as bromide. You have a choice. You either put in the hydrogen at position 1, getting a positive charge at position 2, or you could get hydrogen at position 2, in which case you would have the first position will take up the hydrogen. What's going to happen next? Well, that depends on which carbocation you think will get formed. So which one do you think it is? This one is a tertiary carbocation. This is a primary carbocation. Any ideas from the last chapter? What's more stable? Yeah, tertiary carbocation is 100,000 folds more stable as compared to your primary. So this is way more stable. This will be sort of solely the product that will be, or intermediate that will be generated, and then your Br minus is going to attack, because this carbocation is essentially electrophilic in nature, and you would end up with the Br that could point top or bottom, but that's for another day. We'll talk about that. But notice what has happened. We have added H and Br across the double bond, right? We have added H and Br across the double bond in this case. Hopefully you have been able to identify two things. There are two steps here. The first step is where your alkene is attacking the electrophilic hydrogen. The second step is where the Br minus is attacking the carbocation. So there are two steps. That means if you were to draw out the energy profile, energy being on the y-axis, reaction progress being on the x-axis, how many humps should you see? That is correct. You should be seeing 2 humps in your energy profile, where you will be starting with the alkene. You will end up with the 2-bromo 2-methyl propane molecule. And so, of course, you have used up the reactivity. So that's why there is a difference in the energy. And the fact that the energy is getting released tells us that this is going to be an exothermic reaction. Of course, this is going to go through the 2 peaks for the transition states. Those are your 2 steps, recall. And they are going to be separated by a valley, which is your carbocation intermediate, right? So it will look like this, where the peaks are going to be the TS1, the transition state 1, the transition state 2, and the valley that you have is going to be your carbocation intermediate. This is where you have your product. This is where you have your starting alkene. If you wanted to determine the energy of your transition state 1, that is delta G double dagger 1. If you wanted to determine the energy of your transition state 2, that's your delta G2 double dagger. And the difference in energy, which is this difference, is going to be the delta G0. Okay, so one could say that the energy of the intermediate is always higher than the starting alkene. And we are saying that because, of course, your carbocation is going to be more energetic as compared to the neutral alkene molecule. And as a whole, though, your reaction is exergonic. That means it's going to have a negative delta G value. And so the first step, the protonation of the alkene that you have, that has the highest, notice that has the highest delta G1 double dagger, which means that that would be the slowest reaction. So that will be your rate determining step. So you can determine your rate determining step, which will be your rapid reaction, which one will not be, all of that good stuff. You can determine that from your energy profile as well. Now, the electrophilic addition reactions to alkenes, they are successful, not just with HBr, but also with HCl, HI, though I would say that with HI, you don't typically just use HI. You might see Ki mixed with H3PO4, which will give you 3 moles of this. So that will give you K3PO4 plus 3HI, which is generated, the word is in situ. So it's generated within the reaction rather than taken as is. And that's just because of the high reactivity of the molecule. A typical solvent in all of these is going to be ether. So recall what's written either under the arrow, or if your reagents are written as A plus B, and then on the arrow you could see the solvent. That's a possibility too, and that will give you your products. So just to reiterate, since this can take a toll, again summarizing, we have a two-step process. Step number 1, where you hit your first transition state, is where your double bond is attacking. So that's where your double bond is attacking your HBr. Bromine has gone as Br minus. This is where the bond will break between, let's say, 1, 2, 3. So the pi bond between 1 and 2 is going to break. The bond between 1 and hydrogen is going to be made. The bond between H and Br is going to break as well. That is your transition state. This is the structure of your transition state. Okay? As the bonds formalize, again, that will give you the carbocation like we discussed. That's your valley. That's why that's the bond formalization. Bonds got formed, so a release in energy happened. Notice that your first transition state, your TS1, is the highest energy state. The energy required, that's the double dagger that we have been talking about. And now when the Br minus comes back and attacks, that will be the second transition state, and as that bond formation formalizes, you end up getting your overall product. So this reaction is not just limited to, like I was saying, to HBr. You could do this with HCl, with HI, with water and acid, and each of those will bring in a different reaction condition. Again, to remind you that ether, whenever you have written, the solvent is typically on top of the arrow. Again, A plus B on top of the arrow, and then gives you the products. You can also write it as A, B on top, and then it will be under the arrow. So different ways of saying the same thing, but look at the yields. We are looking at like a 94% yield. That means the majority of your product is going to be the product that you're seeing for this particular substrate. And this was the case where we had the carbocations that you are going to generate is a tertiary carbocation versus a primary carbocation. That is the only carbocation that will form, because that will be 100,000 folds more stable than the other one. If it was a choice between a secondary and a tertiary, some secondary might form, and then you would have two products or a mixture of two products, still the tertiary being the more predominant one as compared to the secondary one. So let's take a moment to write down with a completely new substrate and write down some reactions and try to predict perhaps what the product might be. So HCl ether. Let's try a KiH3PO4. Maybe another one could be H2O with H3PO4. And let's see what you guys come up with. You can pause me and then see whether my products and your products kind of match up. I'm going to follow along. I'm going to try to explain one more time to show you how the double bond is attacking the H plus, and the Br basically leaves as a Br minus that has the capability to generate a tertiary carbocation versus a secondary carbocation. Of course, the tertiary carbocation is going to be more stable, which is where the Br minus is going to come in, is going to attack, and is going to give you the product. Now, when we have the HCl on the other hand, the HCl is going to bring in the H here and the Cl. And in this case, it's a difference between secondary versus tertiary, right? So the major product is going to be the tertiary. Maybe a tad bit of the secondary would get generated. Same would be the case for HCl. Notice how my Cl goes to the tertiary location. The Ki and H3PO4, like we discussed previously, they're going to give you 3 moles of Hi plus K3PO4, and those are going to allow that Hi that is generated. The word is in situ, which means within. So that Hi that gets generated within is going to go through the reaction, and you get your addition of the Hi across the bond. And that ends up giving you your 1-iodo-1-methyl cyclohexane. Now, when H2O and H3PO4, I'm going to just put down the Lewis structure of that so you can follow along the mechanism. The lone pair of oxygen is going to attack the proton. H2PO4 is going to leave, so it's going to generate an equilibrium where you have H3O plus H2PO4 with a negative charge. So now your active species in the reaction is the hydronium ion, aka if you were to write down the mechanism of that, you would be starting with your double bond as your nucleophile that will attack the proton of the hydronium ion. You are going to see the loss of the water. That will generate the tertiary carbocation. And now you might wonder, well, there is water, there is H2PO4 negative. Which one should attack the positive charge? If you're thinking H2PO4, think again, because that is not a nucleophile. It's big and bulky, and one of the requirements of things to become nucleophilic is that they can move around really easy. So it is water which is going to serve as the nucleophile. It's going to attack. You would end up getting OH2, H2PO4 can pick up the proton again, and notice how again your HOH from water has added across the double bond, specifically through that tertiary carbocation. I'm not so sure if you guys are seeing the theme that I want you to see, but really here a theme is emerging. All of these molecules that I showed you in terms of reactivity, all of them are of the kind HX, where X is slightly negative and H is slightly positive. Whenever you have a scenario that you have a molecule which reacts with a double bond serving as a nucleophile, the double bond is going to attack the proton. It's going to release the X minus, and then the X minus comes and attacks, right? That's what we have been seeing. Well, it turns out that the negative end of this HX molecule ends up on the more substituted carbon atom. Notice between the two carbon atoms that I had drawn, maybe position 1 and position 2, the Br, the Cl, the I minus, in case of water as well, all of them showed that the negative end of the molecule went to the more substituted end. The positive hydrogen, on the other hand, stayed on the less substituted end. Same goes in case of HI, same goes in case of water. Long story short, there is a pattern that we have that the negative end goes to the more substituted carbon, the hydrogen goes to the less substituted carbon, or in other words, the carbon that holds more hydrogen atom. I don't know about you, but for me, I like to look at things the way I can understand it. So when I was a student, my takeaway was that hydrogen is going to go on the carbon atom that is rich in hydrogen atoms. The X minus is going to go to the carbon atom which is somewhat poor in carbon atoms because it is more substituted. So it's rich in substitution, it's poor in hydrogen atoms. And this rule is what is called as the Markovnikov's rule. Markovnikov's rule, that's exactly what it states, that if you have an asymmetric or unsymmetric alkene, then the HX type of reagents can react in two different ways, and one is of course more preferred than the other. But Markovnikov was the first person who sort of identified this pattern that the hydrogen attaches to the carbon with most other hydrogens, and the X attaches to the other end. That means with the more substituents or less hydrogen atoms. I kind of used to call it back then with other courses. I used to call it theory of capitalism. Rich get richer, poor get poorer. So the carbon atom which is rich in hydrogen continues to get richer. The carbon atom that lagged hydrogen continues to stay that way. Okay, so that was Markovnikov's rule as he found it. Okay, so let's take a look at 1-pentene with HCl. Hopefully you can see that your two positions where your HCl will come in, those are going to be 3, 4, those are going to be 1 and 2. And so now when the HCl is going to get added, you have your positive charge here versus you could have a positive charge at the terminus. When the Cl has to come in, it would of course prefer to form the secondary alkyl halide as against the primary alkyl halide. So in this case, they're saying that the only product that they see is this 2-chloropentane, not the 1-chloropentane at all. Whenever you have scenarios such as this, where there is only one product and one product alone, we use the word regio-specific to describe that. What that means is that you had the option to form 2, but it was present in the ratio 100 to, they typically say 1, but 100 to 0, you can say that too. If I say 100 to 0, that will become infinite, right? So that's why 100 to 1. That entire molecule, entire molecular population favored only one product out of the two. If you do have the option where you get the major and the minor, so when those are formed, we say that it is a regio-selective reaction. So they could be in the format of 70-30, they could be in the format of 60-40. Long story short, what we are saying here is that you are going to get two products. So if you take the GC of the product mixture out of a regioselective reaction, you are going to, assuming that the entire reagent has been used up, that means that you would get 2 peaks out of your reaction mix. On the other hand, if you have a regiospecific reaction, since that gives rise to only one sole product, assume that the reaction has gone 100%, meaning that the entire reactant has been used up. You should get only 1 peak in GC. I hope that makes sense, that connection makes. All right, so over here, I'm showing you 2 different examples as examples for Markovnikov rule. Notice I have 2-methylpropene, something that you saw before. We have 2 different carbon atoms, one in which there are 2 alkyl groups, the other that does not have. So you have the option to form a tertiary carbocation versus a primary carbocation. And because of that big difference in energy between the two, you're not going to get any of the primary alkyl halide. It's going to go solely to give the 2-chloro-2-methylpropane. If you do the same thing with 1-methyl cyclohexene, it's the same idea, because you have the option to form the tertiary, and whenever tertiary carbocation is there, that typically kind of takes over, and so you are going to see only one product, and so we would say that this is a regiospecific reaction. Now, the last reaction that we have, in that case, we have alkyl groups on both the ends. So it's very similar. That means you are going to end up with a mixture of products. So that is not going to be regiospecific. You would say that that is a regioselective reaction, because you will have to at the end of the day. And so that again, saying the same thing, Markovnikov rule, at this point of time, basically write down only the starting material with HCl and pause me, don't look at the slide, and tell me what the product would be. Go through the entire mechanism perhaps, and then tell me what did you get as your products. So hopefully you can see that your alkene is a nucleophile that attacks the proton. HCl, Cl negative leaves, that gives you the carbocation, which is the T-butyl carbocation, which is the more stable of the two. Primary carbocation is not going to get formed, which is why that particular product is not even pursued. The Cl negative comes back in, that's your transition state 2. The second hump of your energy profile gives you the 2-chloro-2-methylpropane as your final mixture.